Good morning, everyone. Uh, Today we'll discuss about the one of the topic, that is a threshold condition for the laser oscillation, and we'll discuss the laser diode rate equations. My name is Himanshu Nagpal, assistant professor in EC department of AKGEC Kaja. This topic is related to the subject, that is a optical communication. So before we start with the optical communication, we should know about these terms. We should know, that is stimulated emission, spontaneous emission, pumping, and population inversion. And then there is a amplification. So these terms, we should know about these terms before we start with the laser oscillations. So in laser, that is a light amplification stimulated emission of radiation. So in laser, let's say there are number of electrons present. This is a valence band, and this one is the conduction band. The number of electrons present in the valence band, when these electrons or when these material gain energy, clear, then these electrons will excite to the conduction band. Clear? These electrons will excite, goes to the conduction band. Now there are two possibilities, that whether the electron will come automatically. Generally the electron will stay at the conduction band with the range of 10⁻⁹ or 10⁻⁸ second. When it comes automatically to achieve the stability, this electron will come automatically after staying this much of time. Then this type of communication, this type of emission, and when these electrons go back to the initial conduction band and releases a photon after staying a 10⁻⁸ or 10⁻⁹ second, releases a photon, and this is known as the spontaneous emission. Clear? Now if I say this electron which goes back to the at the conduction band, if it knocks out from the conduction band and goes back to the electron by applying another force, means by another photon which strikes this electron, and this electron goes back to the valence band. So this photon has some enough energy that it knocks out this electron, and this electron goes back to this valence band. Then another photon will release, one photon and this photon, they both have the same phase. That means one photon can produce two photons, and therefore, and this process is known as the stimulated emission. Means the electron will not stay more for 10⁻⁸ or 10⁻⁹ second. It has to be less than the 10⁻⁹ or -8 second. Clear? So to stay less than this time, it should be knocked out, and for knocking out this photon have some energy, it knocks out the electrons and produces another photon, and one photon can produce two photons. This is known as the stimulated emission, and both have the same phase, so therefore that is a coherence, and this results in a narrow beamwidth due to the same phase. Clear? So now see, to have more photons releasing, so we should have the number of electrons at the conduction band. So to have a number of electron at the conduction band, we have to provide the pumping, because when the number of electrons in the conduction band is more as compared to the valence band, then only there will be a chance of the maximum probability of the stimulated emission. Then for that process we have to provide the energy, and that is known as the pumping. And when the number of electrons gets more in the conduction band as compared to valence band, and this type of process is known as the population inversion. Clear? Now when this photon further strikes the two electrons at the conduction band, and that will produce what? 4 photons. And when these 4 photons further strikes the electrons at the conduction band, this will produce a total 8 photons. So this is known as the stimulated emission, and due to this we can achieve the amplification. Clear? And this amplification can also be achieved by when these 4 photons are captured inside the cavity, and these 4 photons will further induce the 4 electron produces 8. So these photons, we have to capture these photons, clear, to get the amplification. So to have a amplification in the laser, we have placed the mirror at both sides. One is fully reflected mirror, and another is the partially reflected mirror. Clear? So when the two photons, when one photon produces 2 photons and 2 produces a photon, then these photons will be inside the cavity, and when it then photons will reflect back from the partially reflected mirror and provides a positive feedback. So after positive feedback, by the reflection at the mirror at the either end of the, means this is a fully reflected, means no photon can be produced out from this one, only that type of photons will be emitted from this mirror when the photon has enough energy to cross the mirror. So to have the enough energy to cross the mirror, so means there should be some minimum gain to be achieved by the photon, so that it crosses the partially reflected mirror, and that type of minimum gain, that is known as the threshold gain. So we'll talk about what should be the threshold gain of the photon, so that it will produce a photon from the laser cavity. Clear? And that is known as the laser oscillation. So there should be some minimum gain should be required, have a photon. Means photon should have a minimum gain so that it crosses the cavity from the partial reflected mirror, and that minimum gain is known as the threshold cavity. Clear? So if I talk about a minimum threshold gain with an amplifying medium must be attained such that the laser oscillations are initiated and sustained. This threshold gain may be determining the change in energy of a light beam as it passes through the amplifying medium. Let's say the amplifying medium has a length. This amplifying medium has a length L. Clear? Is filling the region between the two mirrors which have a reflectivity. Each mirror have reflectivity. This mirror has a reflectivity R1 and this mirror, let's say, have reflectivity R2. So fractional loss. So there will be a gain due to the positive feedback. Clear? And that depends, that overall gain, that also depends on the length of the cavity. And there will be loss of the photons due to the reflection by the mirror, and the losses occur in the cavity. So the fractional loss is equal to the by the photons is equal to the R1 into R2 exponential e की power minus 2 into alpha into L. This R1 is the reflectivity. This R1 and R2 is the reflectivity, and alpha is the attenuation in the in the cavity. Okay. Now, if I say the gain after positive feedback, the gain produced by the gain coefficient produced by the stimulated emission is given by the fractional gain is equal to e की power 2 into G into L, because the fractional round trip gain is given by the fractional. So minimum threshold condition will be when both the fractional loss and the fractional gain is multiplication of fractional loss multiplying fractional gain should be equal to 1. Means the fractional gain, that is e power minus e power 2 into GL multiply my fractional loss R1 to R2 into e power 2 into alpha into L equal to 1. And from this we can calculate this R1 into R2 e power 2 into G into minus alpha L. So we can also from there we can calculate the threshold gain. This G can be written as GTH. This GTH minus में alpha into में L is equal to the 1 upon में R is equal to the 1 upon में R1 into R2. Clear? And when it goes natural log of 1 plus में R1 into R2 divided by 1 by 2, and clear? So GTH will be is equal to what? Will be equal to alpha plus में 1 upon में on simplifying this we'll get the alpha plus 1 upon में 2 into L natural log of 1 upon में R1 into में R2. Clear? So this should be the threshold gain achieved by the photon, so that it produces gets out of the cavity and produces the laser oscillations. So this should be the minimum gain to be achieved by the photon to produce the laser oscillations. Clear? So now next one is the laser diode rate equations. From the laser diode rate equation we can also find the threshold current density. Threshold current density we can also find out from this equation. From these, this is the minimum threshold current density required by the laser to have a minimum current. You can say minimum current required by the laser to have a pumping which produces a population inversion and when there is a population inversion, this also produces a stimulated emission. Clear? So minimum current required by the laser to have a stimulated emission, and that is known as the threshold current density. We will talk about this threshold current density in this. Clear? Now see, behavior of the semiconductor laser can be described by the rate equations for electron and the photon density. Now here the electron density is given by N, and phi is given by the photon density. Now as we know that one photon produces a 2 photon, 2 photon can produce a 4 photons can produce a 8 photons can produce a 16. So you can say that there will be a rate of change of photon production per unit time, and similarly there will be a rate of decrease of electron per unit time. Clear? So there will be 2 rate equations for the electron density and the photon density. Clear? So as we know that the photon generation is depend upon what? How much photons are produces, that depends on the current density. हमने current density से कितने electrons दिए हैं उस पर depend करेगा. कितने photons मेरे stimulated emission से produce हो रहे हैं, कितने photons मेरे spontaneous emission से produce हो रहे हैं. क्लियर? तो फोटोन जनरेशन किस पे डिपेंड करेगा? स्टिमुलेटेड एमिशन से जो फोटोन जनरेट हो रहा है, द फोटोन जनरेटेड बाय द स्टिमुलेटेड एमिशन and the photons also generated by the spontaneous emission, because in laser both emission will be occur. Stimulated emission also will be there and the spontaneous, but spontaneous emission has a very less value, has very less role as compared to the stimulated emissions. So the main priority will be always given to the stimulated emission in the case of laser. Clear? And the losses minus में mind the loss of photons due to what? Due to attenuation, you can say, due to the reflectivity at the mirror. Clear? Due to the reflectivity or attenuation. Clear? Now this, therefore, rate coefficient d phi by dt, this is photon density changes with respect to time, is equal to the C n phi. This C n phi represents the photon generation due to the stimulated emission clear, and this is the C defines the C is a coefficient which occupies the B coefficient, clear, which defines the strength of the, this C is the constant that defines the strength of the stimulated emission, clear. Plus में photons produces due to spontaneous emission, and these are the photons which are lost due to the attenuation and due to the reflectivity, and this is minus phi upon में tau into में pH. So this is a change of rate of photon density per unit volume. You can see here that first term depicts the stimulated emission as a source of photons, clear, and the fraction of the photon produced by the spontaneous emission, that is delta into में phi divided by tau pH, clear, and delta is very small because spontaneous emission is very less, so delta is very small. This can be neglected, and the final term in this represents the decay in the number of photons resulting from the losses in the optical cavity, clear. So the electron density, photon density is changes that depends on the stimulated emission plus spontaneous emission minus photon loss. Now how the electron density will also be changes, because as the photon increases, the electron density will also be changes with respect to the time. That depends on the how much electrons are injected into the laser through the current. Therefore, dN by dt is the change of electron density per unit time, that is equal to J is the current density, the electrons injected through the current, that is given by the J upon E into D. This D represents the thickness of the depletion area where the actual recombination take place. Clear? J by ED minus में electron density reduces due to spontaneous emission, and minus में electron density reduces due to a stimulated emission. Clear? Because in the photon density, when electron generates a photon, this factor will become positive in the photon generation, and this factor will become negative in the spontaneous electron injected electrons. Take a depletion of electron, and similarly electrons get also be depleted due to spontaneous emission, and here the photons get added due to the spontaneous emission. Why the delta is? Because delta is there, that is a factor which always less than the 1, because this delta depends on the radiative. This delta depends on the recombination, radiative recombination or the non-radiative recombination. That is why delta is very less. Clear? So now the rate, so you can see the first term indicates the increase in the electron concentration in the current conduction band as the current flows into the junction diode, and the next term, that is the electron loss from the conduction band by the spontaneous emission and the stimulated emission. Clear? Now see, that this rate equation, this is I can say equation number 3, or you can say, now this rate equation can also be used to study the transient and steady state behavior of the semiconductor laser. This Cn, 1 minute. Now see, now to have a steady state behavior, this dN by dt should be equal to 0. So therefore I can say that, and you can say that Cn into my minus tau ph, Cn into my minus Cn phi minus phi upon my tau ph should be greater than or equal to 0. How? Because you can see that this is what contribution of photons due to the stimulated emission, and this one is the photon loss. Clear? You can see here that this one stimulated emission, photon entry into the stimulated emission, and the photon loss due to the, for the steady state behavior, d phi by dt should be equal to 0 and delta is very small, so we can ignore this term. So the Cn phi should also be always equal to the greater than the loss, because to have a laser oscillation, stimulated emission should be greater than the photons produces due to stimulated should always be greater than the photon loss due to the in the cavity. Means this Cn phi minus Cn phi minus phi upon tau p should also always be greater than equal to 0. Therefore Cn minus phi, Cn minus 1 upon tau ph should be greater than or equal to 0. Clear? So if I say what are the minimum number of electrons density required to have a stimulated emission? Clear? So what are the minimum electron density required to have a stimulated emission? So therefore this n can be replaced by nth. So therefore from this equation you can see that Ca into my nth is equal to, should always be 1 upon my tau ph, and this nth gets equal to 1 upon my C into my tau ph. Means this is the minimum threshold condition of electron density required to have a stimulated emission or steady state for the steady state behavior. Minimum condition. Clear? So this, when I'm talking about the electron density, therefore corresponding to this we can say there should be a current density, minimum threshold current density. For minimum, therefore minimum threshold current density will be equal to what? From this equation you can see that dN by dt should also be equal to 0. So this J can be written as JTH divided by ED. Clear? Spontaneous emission is very less, so Cn phi is equal to, you know that Cn phi is what? C into n 1 upon tau ph. So you can see that C threshold current density EJTH by ED, when threshold condition is minimum current density, at that point phi is equal to just about the photon produces. Clear? Minimum photon produces at that time, the phi is equal to 0. So therefore JTH divided by ED is equal to the nth divided by tau into my SP. Because for LED we do not have a threshold condition, but for the stimulated emission, for the laser, we should have a minimum current density required to have a stimulated emission or the laser oscillations. So that's why spontaneous emission will always be there. Clear? So JTH by ED is equal to nth by SP. Now put this value in equation number 1. This. Clear? Now see, on putting this equation, 0 is dN by dt is equal to 0. Therefore J by ED minus में n by tau sp है ना, this minus n by tau sp is equal to minus में JTH by ED minus में C into में nth into में phi s. Clear? Now on solving this equation you will see that phi s equal to 1 upon में C into में nth j minus में jth upon में ed. Now you will see, has put the value of C into में nth. Now put the value of C into my nth. Where C into my nth was there? C into my nth. That is 1 upon my tau ph. So put this value. You will say here C into my nth is equal to 1 upon my tau ph. Put this value. C upon my nth is equal to 1 upon my tau ph. That is tau ph upon my ed. J minus my jth. So minimum threshold. So to have a photon density, steady state photon density, this is the minimum threshold current density which you have to require, and this is the current density which we can apply. Clear? The photon density phi s cannot be a negative quantity. This phi s cannot be a negative quantity. It should also be greater than equal to 0. So to have a greater than 0, this phi s, so to have this phi s greater than equal to this current applied should always be greater than the threshold current density. Clear? Now as each photon has its energy, therefore it is possible to determine the optical power density related to the energy of photon. So this gain, this threshold gain, to be achieved by the, when I have talked about the initially threshold condition for the laser oscillation, this is the threshold gain to be achieved by the photon to produce a laser oscillation. That is, should be always be depend upon the initial threshold condition, threshold current density required to have a stimulated emission. Clear? And that is the factor multiply में beta. So beta is the gain factor which is depends on the specific devices. So just put the value. So minimum threshold density JTH is equal to 1 upon beta into my GTH, and put the value of GTH. As we know, the threshold current which we required, that is alpha upon 1 plus 2L into my natural log of 1 by R1 into R2. Put this value here. So we will have a minimum threshold condition, minimum threshold current density required, that is equal to 1 upon beta alpha plus 1 upon 2L into my natural log of 1 upon R1 into my R2. Clear? So injection laser diode characteristics. So before the threshold condition, before the threshold current given to the device, spontaneous emission will be there, and after threshold condition, threshold current which you provided, after threshold condition current, then the stimulated emission will take place, and it gets current get suddenly rises. A light photon generation of photons suddenly gets rises in stimulated emission. Today we have discussed about the laser diode rate equation, and before the laser diode rate equation we have discussed about the threshold condition. Minimum gain threshold minimum gain achieved should be achieved by the photon to have a laser oscillation. We have discussed. So thank you for the today's lecture. Okay. And the book, the slides which we have prepared from the book, that is the Optical Communication by the John M. Senior. Thank you.